Hello and welcome to TidyX episode 99. TidyX is a screencast where we go through and explain how our code works. My name is Els Hughes, and you can find me on Twitter at Els_Hughes.
And my name is Patrick Ward. You can find me on Twitter at OSPPatrick and at Tidy_explained is where we both are on Twitter. Tidy.explained at gmail.com is where we both are on Gmail. You can open up an issue on the GitHub repo. You can go to YouTube, like and subscribe at the bottom, drop a comment, a question. And we also have a Patreon page, which is super awesome because if you like the work that we're doing and you want to support us and you want to buy us a cup of coffee or a beer from one of our favorite brewers, we're totally into that and we'd appreciate it.
For sure.
And here we are. We are on the doorstep of 100 episodes.
On the doorstep. We're almost there. I'm really excited. Really excited for our next episode. But we've got this episode that we got to get through right now. So
and this episode is what is the probability that we do 100 episodes given we've already done 99?
I don't know.
It's probably pretty
comments
high.
Down below.
Pretty high. It's pretty high. Yeah.
Yeah. So as a hint from that, we are going to be looking at Bayes. We've kind of hinted that a little bit the last couple episodes. We've been talking about distributions. We've been talking about how to do resampling. But now we're going to get into Bayes and Bayesian statistics. Patrick, do you have anything you want to share as I go to share the screen with everybody?
Yep. So we've gone through building distributions now. We've gone through resampling. We've gone through simulation. And now we're ready to give sort of this intro to Bayes, what I call the Bayes 6. And we'll just give some overview of what Bayes is, thinking in Bayes, some general notes. And then we'll get into this over a series of 4 or 5 screencasts where we're going to apply it to things that are more interesting to us than flipping coins and diseases, and that would be sport, of course. So, but we're gonna go through some general concepts of Bayes, and we're gonna walk through the sort of classic examples that you'd see in 99 out of 100 books that you pick up that start in Bayes.
What is the probability that it's a Bayesian book given?
Right, exactly. So, some notes, the basics. I'm not going to beat this up. If you want to read a great book on this, there's a book by Aubrey Clark. By Aubrey Clark called Bernoulli's Fallacy, and it's all about this sort of duel between frequentist and Bayesian statistics over the years. At a high level, frequentist statistics, this is traditionally what most of us are taught when we go to university. This was what my stats classes were all about. It's based on the idea of that probability represents the frequency with which something happens. And so it answers the question, what's the probability of the data given my hypothesis? So we basically have some data. We have a hypothesis. We usually have competing hypotheses, a null and an alternative. And the idea is to look at our data and answer the question, what's the probability of observing whatever it is I observed, or the size of whatever it is I've observed given chance alone, right? That's our p-value. That's frequentist statistics. That's what we're looking at. In Bayesian statistics, it flips that problem. So it's actually concerned with how probabilities represent our uncertainty about information. And it answers the question, what's the probability of my hypothesis given my data? So this is saying, you know what? I'm actually walking into this situation with some prior knowledge, with some expectation, with some sort of intuitive feeling about what I should be seeing. And now I'm going to observe some data. And how does that update my knowledge of the world? And that's really what Bayesian thinking is about. It's named after Reverend Thomas Bayes. It's a mathematical approach which allows us to interpret observed data within the context of our prior knowledge, assumptions, or experiences. And then our prior knowledge is updated using what's called Bayes' theorem, which is a way of organizing conditional probabilities. And that's what the vertical bar means. The vertical bar is basically spoken as given. So the probability of A given B, the probability of A conditional on the fact that we know something about B, is equal to the probability of B given A multiplied by the probability of A divided by the probability of B. Okay, lots of letters. What does that mean? So let's break this down within the framework of how we would think about it not necessarily how we would think about the math, but how we would think about this as a human. Probability of A is our prior knowledge. So I'll give an example. I'm going into this and I'm saying, I know something about Major League Baseball hitters, and I know that on average, the average Major League Baseball hitter has a batting average of 0.26. Okay, so he's a 260 hitter. The likelihood, probability of B given A, is what I've observed. So let's say the batter goes out, he's new to the league, and he goes 5 for 10. Do I believe that this batter is a 500 hitter? Is it possible that I'm dealing with the next Ted Williams? Maybe. But I don't want to be so bullish on that. And in some way, I want to evaluate what I've observed, weighted by the number of times I've observed it, within the context of what I know about the population he's part of. And that's my prior knowledge. The population he's part of is on average a 260 hitter. And so when I combine those bits of information, it allows me to get a better representation of what I might think about this batter. Now, initially, he's going to come out being still above average. He'll be above 260. But he won't be so far above 260, nearly 2 times above 260, that it drowns out everything else. We're going to constrain our knowledge about this individual because we have few observations. And as we get more observations, we're going to see his probability dance up and down until we come to something that is a little bit more stable and is representative of his true talent and ability. And so probability of B, the denominator, is what's referred to as the data. And that's the normalizing constant. And it ensures that all of the outcomes we're looking at obey the rules of a probability distribution, which means they have to sum to 1. Probability only goes from 0 to 1. It can't go above that. So it has to sum to 1. So we're evaluating what we saw based on what we know. We're putting all that information in, and we're dividing by this normalizing constant to get everything summed to 1. And that produces our posterior probability. This is the final knowledge that we're taking forward on this player. And now we're going to observe his next 10 hits. And that's going to, this posterior probability becomes our new prior. And every time we see new information, we have a new posterior, which means it becomes the new prior. And that gets updated again and then again and again. And this can go on in perpetuity as we learn new information. And so I just have the equation down there, probability of B, the normalizing constant can be a little messy for people to think about. This is what it looks like when we're dealing with these discrete cases. It's different if it's a continuous distribution. You have to do a bunch of integral math. But we're going to talk about simple ways of doing that. We're going to write some simulations for that in later. We're going to leave that. There's also something to know is that you don't always need probability of B. There's times when you don't have the denominator. And so you can use this approximation of Bayes where you only use the numerator, and we'll use Bayes factors and odds ratios to compare two potential outcomes. And we're going to talk about that later on down the road. That's the probability of B. It's the probability of our likelihood multiplied by our prior plus the probability of B given not A times probability of not A. So basically the probability of seeing that same data, but not the same outcome. Okay. So let's get into an example. And this is the classic example. Most Bayes books will use this example within the context of breast cancer treatment or breast cancer testing. So you feel ill. Ellis is ill. He goes to the doctor and the doctor says, geez, you might have this very rare, but potentially deadly illness. And we want to test you for that. And I just got to let you know that this test has correctly identified 95% of the people that have been positive with this disease. And that's referred to as our sensitivity, right? The probability of ruling in those that actually have the disease. And then he also goes on to tell you that, this test is also successful 95% of the time at identifying those that are negative with the disease. That's our specificity, the ability of the test to rule out those that are not sick. Okay. And so the doctor returns the test, gives Ellis the test, returns the test, and says, hey, you're positive for this illness. And you want to know, and what the doctor wants to know is how probable is it that I have this actual illness? And this is what's called in medical research as the base rate fallacy. And they do these polls where they ask doctors like, well, if you tested 100 people like Ellis, how sure are you that the person has the disease when it comes back positive? And they say 95%, they spit back the sensitivity, which is not true. Unfortunately, neither sensitivity or specificity tell us about what we really want to know. What we really want to know is the probability of illness given a positive test. And that's where we can apply Bayes' theorem. And we use our prior knowledge about the base rate of this rare but potentially deadly disease, which is only 5% in the population. And we're going to apply that and update the information of the test saying that Ellis was positive given what we know about the test sensitivity and specificity, and it's false positive and false negative. So before we proceed on and do the actual R coding, let's write down the information that we know. We know that the prevalence of the disease or the illness is 5%. Okay, so that's the P illness. That's our prior. The probability of a positive test given that the person is ill is 95%. That's our sensitivity. We've talked about that above. The probability of a positive test given that you're not ill is 1 minus 0.95. It's 1 minus our sensitivity. That's a false positive. The test said he was positive, but he didn't have it. The specificity is the probability of a negative test when you have no illness. This is our specificity. We talked about that above, ruling people out. And therefore, the probability of a negative test given that you do have the illness is a false negative. It's 1 minus 0.95. It's 0.05, right? So this time we said, hey, don't worry, you're not sick, when you actually were. And then the complement to our probability of illness, so if the prevalence is 0.05, then the prevalence of not having this illness is 0.95, okay? So 1 minus, that's the complement. So now we know all this information. Let's return it in that Bayes formula, and then we'll code it up. So if we apply this, we're basically trying to figure out our posterior probability, which is this conditional statement, probability of illness, given that the test is positive. And we get the following on the right. We get the probability of a positive test, given that you have the illness, multiplied by our base rate of the probability of an illness, divided by the normalizing constant, which is the probability of positive test given the illness, multiplied by the probability that you have an illness, plus our false positive, right? Our probability of a positive test given that you weren't ill, multiplied by the probability that you don't have the illness at all, the complement of the illness. And here we go. We're going to write this out into probabilities. So we put it all into a cool little R script here. And at line 79, that's the denominator. So we should probably put a little hashtag above that and say that that's the denominator, right? That's the normalizing constant. That's PB, right? Probability of B in the traditional Bayes theorem. So we do it all in one step so that it's just nice when we apply Bayes theorem down at the bottom. We now have our likelihood, probability of a positive test of giving you have the illness, multiplied by our base rate, probability of an illness, divided by our probability of the data, our normalizing constant. And we see that there's only a 50% chance that you have the illness, not 95%. So, the doctor probably gave this test to Ellis as a quick and dirty, at the urgent care, let's get some information. This test is relatively cheap. And if it comes back positive, if there's now a coin flip chance that you have the disease, we might send Ellis for a more invasive test or more rigorous testing and try and get more information and rule out potentially other things so that we know what we're dealing with. Mm-hmm. And that's the way that Bayes' theorem is often presented when talking about illness in most of these books. Mm. The other example is coin flipping. And coin flipping is like one of the traditional, Renaissance gambling type of dice, and coin flipping are always like the traditional gambling type of things that Bayes is applied to. So let's go through this. We have a coin and we flip it 10 times and we observe 3 heads. And so we want to know the question, well, what's the probability that this coin is weighted towards it? What's the probability that we're dealing with a potentially weighted coin, a non-fair coin? And we're going to start with what's called a flat prior. So this is the most contentious thing in Bayes, is this idea of the prior. How do you get the prior? The prior can be our intuition or from domain experts. The prior could be from previous research, where we've seen some data and we've seen some observations and we have a general idea of where things are coming from. Or you can assign the prior based on being uniform or weak, what would be called like weakly informative, not overly committed in one direction or the other, where you let the data speak for itself. But more often than not, we're coming into the conversation with some prior information. So we're going to try and tee this up here using Bayes' theorem to understand if the coin is fair, given we saw 3 heads out of 10. And flipping coins is a 2-outcome event. It can only be heads or tails. So it's a Bernoulli trial, and we do several Bernoulli trials. So we're going to use the binomial distribution to represent our likelihood. Remember, our likelihood is the observed data, the 3 out of 10. So how are we going to do this? The first thing that I'm going to do is I'm going to set up this probability grid. So I'm going to create a sequence of numbers from 0 to 1 in 0.1 increments. And so these are the probabilities of this coin being a bias coin, okay? And we're going to set up a uniform prior. So basically we're saying every one of those possible outcomes is equally potentially the outcome or the true weighting of the coin. So we're going to give each one of them 0.1 so that they sum to 1 and obey a probability distribution. And then we put them together in a data frame called coin. So now we have a probability, a potential probability of the coin being weighted. We have a prior for each of those potential probabilities. In this case, it's all equal. And now we're going to add in our likelihood. So remember, the likelihood is the probability of the data, 3 successes in 10, right? Given our hypothesis. And in this case, our hypothesis is each one of those probabilities in that P grid in column 1. And so we're going to use the binomial distribution to say, hey, binomial distribution, what's the chances that I see 3 successes out of 10 trials if my prior is that there's a probability of the coin being 0 or being 0.1 or being 0.2 all the way up to 1 in those 10-point increments. And that's what we get there. We get this string of likelihoods that we put into our data frame. And so now we have a data frame that looks like this, and we're ready. So we have a hypothesis in column 1. We have our prior knowledge, which is uniformly distributed in column 2. And we have our likelihood, our observed data in column 3. And we're ready to get our little Bayesian engine going here. We're going to multiply the prior by the likelihood. That's the numerator. And that's going to be unstandardized. Remember, it's not going to sum to 1. And we're going to see that in a second. And now we're going to standardize it. How do we standardize it? We divide by the data. And what is the data? It's the summation of all of those unstandardized posteriors. So now we're just going to sum those up. And now we have this posterior probability that the coin is weighted in one direction or the other, in this case, weighted towards 30%. We let the data speak because the prior was uniform. We can prove that the unstandardized posterior is not a probability distribution because when we sum it, it doesn't equal 1. But when we sum the standardized posterior, we get 1. And we can view both of these cool things here in a traditional plot. Boom,
Boom, boom.
boom. And so now we have a prior that was uniform, and now we have a posterior. And so what do? That posterior becomes the new prior. And we're going to flip 10 more times. Ellis, do you want to take us through 10 more flips with our new updated prior?
Let's flip it 10 more times, and let's say that we see now 6 out of the 10 times we flip coming up heads. So now we have 20 flips total. But we have this prior going on. So we're going to recreate our P grid. So this is from 0 to 1. We're going to pull out the prior from the last 10 coin flips. And now we have our last prior set. We're going to recreate our data frame. And this time we're going to call it coin second flip. And so we have our P grid. So the probability of it coming up 0.1, 0.2, 0.3. And this is our last prior that we calculated. But now we're going to set success to be 6 and trials to be 10 and run it back through the D binom to get the probability given 6 successes and out of 10 and get the probabilities out of that. So that updates our likelihood. So we end up with that same sort of data frame where we have the P grid, the prior, and our likelihood. We go through the exact same steps that we did before where we get our unstandardized posterior, which is the prior times our likelihood. And then we're going to standardize it, dividing by the summation of the posterior, or the unstandardized posterior, Round that, and run it again. So here you can see that this is our new posterior, and this is our prior from the last 10 coin flips. You can see it's kind of moved more towards the middle to back up to 0.5. So now we're going to run this through a ggplot so we can visualize the two overlaid. So we're going to take the coin second flip, we're going to take out the p-grid, the posterior, and the prior. We're going to pivot longer by the posterior and the prior, so then the values, the column names will go into the params column, and the values that are inside of posterior and prior will go to the probability column. We'll throw it into a ggplot where the x-axis is the probability grid. We're going to create columns where the y, so how high it goes, is the probability, and the fill is going to be based on the param, and then we're going to dodge them. That means that we're able to have two bar charts, two bars next to each other. We're going to color them, so the posterior is going to be pale green, and the prior is going to be light green, or light gray. And then we're going to scale the x-axis to be percentages as opposed to like 0.1, 0.2. Now it's going to be 10, 20, 30. Just for visual sakes, let me pull that over so that it's a little bit easier to see. Let's call dev.off because sometimes things get funky.
There we go.
There we go. So
that's a cool grid. Yeah, it's a cool
plot. So you
plot.
can see that the gray piece is from our last 3 out of 10 successes. As you can see, it was pulling towards the left here because it only came up 3 times then heads. But now that we have 10 more coin flips, it's actually, and it came up 6 out of 10, it's pulled it more towards the middle because it's more, now that we have more data, we're more likely to see that it's going to be evenly distributed.
And you could see there's a lot of, now remember, these are, like we talked about last time, these are discrete outcomes, 0.1, 0.2, 0.3. This is not a continuous distribution. So this is probability mass, and there is a lot of probability mass around, around that 0.33, and also all the way up to just under 0.5. If we flip this another 5 times, we might see the probability mass shift even more and get us back towards a 50-50. So that's what happens when we start out with a uniform prior. We basically say, we're not going to commit this in any way. Let the data speak. What if we want to start out with a prior? What if we're like, you know what? I haven't seen too many quarters that are biased. I think they're mostly 50-50. I'm going to create a probability grid. And now I'm going to create a prior that weights each of those probabilities in a way that says, I want to put more mass on the potential that it's right around a 50-50 coin. I want to say that, you know what, there's probably a good shot that this is right around 50-50. And we could see that there. I use dBinome to weight that probability grid and say, hey, I want to commit myself to saying this is probably a fair coin. Okay. So we could plot that and kind of look at this simple histogram of this. And we see that most of the mass is right around 50-50, and 0.4 and 0.6 it starts to fall off. We observe our 3 out of 10 observations, 3 successes, 10. We create our likelihood, and we have our table here. So now we've got our hypothesis, our prior, our likelihood, and we go through all our same steps of our Bayesian engine. We're creating our posterior, hit enter, and now we have this cool distribution that looks like this, where we started out by saying it's a 50-50 coin. We can see how it's normally distributed in gray. And now we saw 3 out of 10. And so the posterior got yanked down just a little bit below 50%. And now there's more mass just below that. So it's saying, oh, maybe this is kind of a fair coin. And then we'd flip it again. And you could see what we're saying. We're not going to go through this again, but you can go through this as many times as you wanted. The last thing we'll touch on, and then I'll leave you with a teaser for future episodes to come, is this idea of sampling from the posterior. So this is overkill for our example here of simple flipping coins. We don't need it. But sometimes in more complex models, and Bayes can get very complex at times, and very complex hierarchical models, the posterior distribution is too complicated. And so in order for us to understand it, we have to create samples from it to get a sense for the data that we're getting back returned to us. So I'm going to do that here. I'm going to use our sample function, which we introduced you to last time when we talked about resampling and simulation. And we're going to create 10,000 samples from the posterior distribution. And so how am I going to do this? I'm going to create my sample by saying, I want to sample that probability grid. I want to sample all my potential hypotheses, but I want to weight them relative to the posterior, relative to the outcome that we saw once we combined our prior with the observed data. I'm going to do it 10,000 times, and I have to use replacement equals true because there's only 10 observations, so I have to have replacement equals true for this to work. And I run that, and I get this string of 10,000 resamples from that probability grid, from our hypothesis grid, weighted towards the posterior. I'm going to do the same thing for the prior so that we have something to plot. So I created 10,000 in the same way. And now we're going to create two little histograms. I'll just use base R. So there's one. We saw that before. That's 50-50 shot. And the next one, we see the 3 out of 10. And now we see the weight coming in just under 40%. There's a little bit more of a bias towards the left of the distribution here now, and the distribution has shifted a little bit, and that's how we sample from the posterior. And the thing that I'll leave you with before we move to next week is that we're dealing with discrete outcomes. So remember, probability mass, but we might not always be dealing with discrete outcomes. We might be dealing with any value between 0 and 1.0. We could be dealing with 0.000001. Right? And so we might be dealing with a continuous distribution that is bound between 0 and 1. And next week, we're going to get into ways of dealing with that when you're dealing with probabilities by introducing conjugacy and the beta distribution and conjugate distributions. And then we're going to take that through to counts and rates and normal distributions and Gibbs sampling and all that fun stuff. But that's where we're going to leave it at today on the doorstep of episode 100.
All right. Episode 100 is going to be a doozy. Definitely tell everybody that they need to join us and watch episode 100 next week. But that is a little bit of an introduction to Bayes. I felt like I learned a lot. Once again, Bayes is one of those things that I feel like is very interesting, and I vaguely understood coming into this. Patrick did a really good job for me as we were going through this to really help me solidify my understanding of this and go, it's really taking what we think we know, assigning data to it, and updating what we think we know based on this new data.
That's it.
If you needed to punchline that's what you got to do. All right, but thank you all so much for joining us for 99 episodes. This has been wonderful. As always, you can find me on Twitter at Ellis_Hughes.
And I am on Twitter at OSPPatrick, and Tidy_Explained is on Twitter at Tidy_Explained. Tidy.explained@gmail.com is where you can fire us an email if you'd like. You can always open up an issue on the GitHub repo. And then, of course, the YouTube channel, you can go ahead and like and subscribe and punch in a comment down there if you enjoy what we're doing and you'd like to contribute to our hydration status. Our Patreon page is always open, and we will enjoy a coffee or a beer if you so choose to buy us one. And that's it. 100 episodes is coming up. Thanks a lot for listening.
Thank you all so much. Keep on exploring your world.